I hope you can see that I did not really want to drive any faster along this track, even though this Range Rover is designed for off-road capability. In fact, all cars have to be designed to cope with vibration and disturbance from a rough road surface, although not as bad as the track I've just come along. This is a matter for analysis and also, most importantly, for development testing. In this program, we're going to show some examples of vibrating systems and introduce the important concepts. We're also going to show a classic set of tests carried out by Dudley Thompson with the Rover Saloon, demonstrating the importance of suspension design.
Well, that was a much rougher road than you would normally expect to have to drive over. In fact, that track was part of a proving ground designed to push car suspensions to the limit. And yet it was still a pretty smooth, comfortable ride, the result of years of development. People probably first started to think about isolating their passengers from the road in the days of the stagecoach. We've come a long way from the simple cart spring to the complex arrangement of links, springs and dampers that go to make up a modern car suspension. This program's about vibration isolation, the sort of thing that we take for granted with a modern car. But take a look at this. In this car, we've modified the suspension. The characteristics aren't quite right. And watch what happens when we take this one down the track.
Well, in order to understand the problems of vibration isolation, we must first get some insight into the nature of vibrations themselves. Take a look at these, a range of vibrating systems. And each individual system has its own particular frequency of vibration. For example, this pendulum performs one oscillation about every second. We say that its vibration frequency is 1 cycle per second, or 1 hertz. On the other hand, this executive toy has a vibration frequency of about 2 hertz. Each individual system has its own characteristic frequency, and we call that frequency the natural frequency of the system. So what are the essential physical properties of these systems which cause them to vibrate?
We can answer Tony's question by looking at this spring mass system. It has several modes of vibration. It can vibrate up and down like this, or it can vibrate to and fro like this. And both modes can take place simultaneously, like this. That was a pretty complicated motion to analyze, so I'm going to concentrate on just one mode, the main mode for a spring mass system, this up and down vibration. So what is it about this spring mass system which makes it vibrate in this way? When the mass is displaced, there is a force exerted by the spring on the mass trying to pull it back. This restoring force always acts towards the equilibrium position. When the mass reaches the equilibrium position, it carries on through, because it has a velocity, and the force acting on the mass at that instant is 0. The mass thus continues to vibrate to and fro under the action of the spring restoring force. So the essential feature of this oscillating system is the restoring force, due to the spring acting on the mass. In fact, all vibrating systems have this common feature of a spring element and a mass.
Well, all of these physical systems look quite different, but they can all be modelled by a simple spring mass system. By changing the spring stiffness and the mass, we can control the natural frequency. And in this way, we can model any vibrating system by a spring mass model. So now let's look at the behavior of an ideal spring mass model and see what it looks like. We can see this on the displacement time graph. On the screen, you can see the displacement time graph for just over 3 complete oscillations. But of course, the ideal system that we're modeling here would continue oscillating at this frequency indefinitely. And different free oscillating systems have different natural frequencies. In this case, the frequency is double the one we saw earlier, twice as many oscillations per second. But now let's go back to the original system, the one with the lower frequency. The maximum extent of an oscillation about the equilibrium position is known as the amplitude. This can be seen as the peaks and troughs on the displacement time graph. Well, those displacement curves are typical of the behavior of an ideal spring mass model. But remember that all vibrating systems have their own natural frequency. And that's a problem which engineers have to take into account in what are sometimes quite unexpected circumstances. The Tacoma Narrows bridge disaster is a classic lesson for engineers in how not to design bridges. The torsional oscillations of this bridge, stimulated by certain wind velocities, eventually oscillated the bridge to failure. Suspension bridges nowadays are usually modelled in wind tunnels before final construction. The same sort of problem has been encountered with tall, regular structures, such as chimneys or cooling towers. Well, the designer ignores oscillations at his peril. Even when a system is not being specifically designed for vibrations, the possibility must always be borne in mind. Well, where have we got to so far in our picture of vibrations? Well, we have a model of a vibrating system, a spring mass model, in which we can identify a restoring force and a mass. And we know about natural frequency and amplitude of our oscillation. But our model, as it stands, requires that the oscillations continue indefinitely. And clearly, this is not the case in practice.
For example, our spring here has come to rest. What extra factor do we need to include in our model to take account of this effect? The missing factor in our theoretical model is damping. So we must include in the model not only the restoring force and the mass, but also the damping force. This system here was quite lightly damped. So to see the effect more clearly, I'm going to put a physical damper onto it. This is simply a plunger which can move up and down in a tube. And I can vary the damping effect by changing the size of the holes at the bottom. I'll attach it to the mass. And we'll see that the damping force is increased and the amplitude of oscillation dies away quite quickly. In fact, I can increase the damping by making the holes smaller. If you look at the effect, the oscillations die away even faster. So now let's look at the theoretical behavior of damped systems. We started with an undamped system. Taking damping into account in our model, the effect is to cause the amplitude of oscillation to die away. Greater damping decreases the amplitude more rapidly. The mass only overshoots the equilibrium position a couple of times here. increase the damping still further, and there's no overshoot at all.
Can we use the idea of a mass spring damper model to help us understand the difference between those two suspension systems? Well, firstly, we need some way of actually measuring the characteristics of the two suspensions. Well, motor manufacturers use rigs like these to study vibration isolation. Road profiles are stored on magnetic tape, and the tape then used to control a flow of high-pressure oil to these actuators. Vibration isolation is about the amount of motion we get at the body compared with the motion we get at the road. These transducers provide us with signals which are proportional to those displacements. So during testing, we can get a measurement of the relative motion of the two. And we can look at the output from those transducers on an oscilloscope. This is the car that didn't perform so well on the track. And we can see the displacement time curve for the car body on the oscilloscope. So that shows the characteristics of the modified car suspension. What happens if we perform the same sort of experiment on the unmodified car? The oscillations die away very quickly. I'll do that again, and this time, look at it on the scope. So how does that compare with the trace we took from the other car? This is the trace we took from the first car. That's the one that didn't perform so well on the track. You can see that the amplitude dies away over about 10 oscillations. In the second car, this is the one that performed well, the oscillations died away almost immediately. So in fact, the difference between the two suspensions is the degree of damping. The one that handled well is more heavily damped.
A spring mass damper system responding to a continuous input disturbance. Well, instead of displacing the system just once from its equilibrium position and watching the response, as Dudley did when he bounced those cars, here I'm putting in a continuous sinusoidal disturbance at a set frequency. And you can see the displacement time curve of the input disturbance on the oscilloscope. It's sinusoidal with a constant amplitude. And below is the output response displacement time curve. The output response is also sinusoidal with the same frequency and a similar amplitude to the input. So here we have a way of continuously recording the response of a vibrating system to an input disturbance. And that's the kind of information we need to design vibration isolation systems, the relationship between output response and input disturbance. For example, if I were to increase the frequency of the input disturbance to a higher value, the system goes into rather drastic oscillations. And this shows up as a large output amplitude in relation to the input. So the system behaves quite differently for different input frequencies. Well, I'm going to run the experiment again, but this time, instead of putting in a constant frequency, I'm going to gradually increase the frequency of the disturbance and measure the output response over this range of frequencies.
Well, that output response curve is rather intriguing, so we'll just take a closer look at those oscilloscope traces. Here is the input disturbance. Constant amplitude with steadily increasing frequency. And you can see this effect by the bunching together of the sine waves as we go to the right at higher frequencies. And below, the output response. The output amplitude increases rapidly with frequency up to a peak and then dies away again. This peak is associated with the rather extreme oscillations you saw and is characteristic of a phenomenon called resonance. It's a condition which designers try very hard to avoid. In fact, this peak occurs at a particular frequency for a given vibrating system. And that frequency is called the resonance frequency of the system. So by performing experiments like this one, designers can find out when those resonant conditions exist, although they usually present their results in a slightly different way, in the form of a graph showing the ratio of the output amplitude to the input amplitude plotted against frequency. This ratio of output amplitude to input amplitude is called the transmissibility, and the curve produced the transmissibility curve. So what do you think the transmissibility curve for this particular system would look like? We can perform the experiment again and plot the transmissibility curve on the oscilloscope. The transmissibility curve is a vital piece of experimental information for the designer. It shows the relative magnitude of the output response in relation to the input. It also shows the resonance frequency. For example, for our experimental setup, the transmissibility at low frequencies is about 1, rising to about 6 at resonance, and falling at higher frequencies. You may have noticed that this transmissibility curve doesn't have quite the same smooth form as the ones shown in the unit. This one, for example. The difference happens because the measured curve was plotted from measurements made while the frequency is increasing. It includes a transient effect. The theoretical curve is calculated for a series of constant frequency values. In practice, the more slowly the frequency is increased while the response is measured, the closer the measured transmissibility curve will be to the theoretical form. Knowing the transmissibility results, we're in a better position to make design adjustments to avoid resonance.
Let's try the same sort of experiment with the two cars. We're going to apply a sinusoidal input displacement here of constant amplitude but steadily increasing frequency, up to about 10 hertz. That's rather like driving over the test track that we saw earlier at steadily increasing speed. Remember, this is the more lightly damped car. Being lightly damped, the transmissibility curve is quite peaked at resonance, as you'd expect. Let's have a look at that again. Well below resonance, the input and output move together. At resonance itself, the transmissibility reaches a maximum. And at frequencies well above resonance, the transmissibility drops off quite dramatically. The output amplitude is very small compared with the input. So how about the damped car? As before, we'll increase the input frequency at constant amplitude. And you can see what the transmissibility curve looks like in this case. Well, as you can see, the transmissibility curve is much less peaked than that of the lightly damped car.
Well, I hope that's given you some insight into the nature of vibrations. We've looked at some of the characteristics of undamped and damped vibrations. Finally, let's take a look at another vibration problem.
This new design of radiator performed surprisingly badly. After quite short periods on the proving ground, it started to fail down the edges of the honeycomb, here. Well, what caused the problem? On the face of it, a radiator isn't very heavily loaded. But let's look at that vibration again. This rig is simulating service conditions, and the radiator responds with a large amplitude of oscillation. The rig was used to measure the transmissibility, just as we did with the cars. And the curve looks like this. There's a sharp peak at the resonant frequency of around 18 hertz. And that's where the problem lies. A large amplitude of vibration is causing the brazing to break down the edges of the honeycomb. So what could the engineers do? They don't particularly want to change the design of the tubing, because that would affect the heat transfer characteristics. And as a radiator, they're quite happy with it. What they decided to do was to increase the damping. And they did that by clamping the honeycomb much more firmly between the top and bottom plates. And this design of radiator may not look very different, but let's look at the transmissibility. That sharp peak has been greatly smoothed out. Less amplitude of vibration, less stress on the honeycomb, and the new design has got a life which is over 5 times the original. So that's not a bad return for the investment of a little bit of vibration theory.